Next chapter is fault analysis. We'll just introduce the chapter today and we'll continue the discussion in the next class. So why we do fault analysis? The main purpose of fault analysis is to design the ratings of switch gear. Is to design the rating of the switch gear. Understand? So what is switch gear? Suppose you are protecting one transmission line, one transformer. How you will be protecting? You will be protecting with the help of a circuit breaker and a relay combination. Circuit breaker and relay. So whenever there is a fault, your relay will sense the fault and your circuit breaker will be tripped. Circuit breaker will isolate the fault. Okay. Suppose in your house you are using a 4-ton AC. And for that 4-ton AC, you are using a 10 ampere or say 20 ampere MCB to switch on to protection. Okay. If a dead short circuit happens inside that AC, let us assume the fault current is the highest fault current that can flow through that AC momentarily is 10,000 amperes. If there is a short circuit in the AC, it can carry a fault current of 10,000 amperes. So when you are putting the circuit breaker, that is MCB, you have to ensure that the breaking capacity of that circuit breaker, breaking capacity, if you have MCB in your house, just go and look. First, there will be one reading called 25, C25, C10, C12, C32. That is the normal current rating. When I teach circuit breakers, I'll explain with figures. But below that circuit breaker, there will be a very small rating where they might have written 10,000 ampere or 6,000 ampere or 20,000 ampere like that. The small number that is mentioned below, that is called breaking capacity. So when I'm keeping my 4-ton AC, here my manufacturer told that if short circuit occurs, the highest fault current that can flow is 10,000 amperes. Then my circuit breaker rating, which I am keeping to protect it, should have breaking capacity more than 10,000 amperes. If I keep a breaker which is having breaking capacity of 6,000 ampere, when fault occurs, before AC, your breaker will get damaged. Your breaker will fail. Okay. So why fault analysis is important? If a fault occurs at a particular point in power system, if we estimate the highest fault current, what will be the highest fault current that will flow? Then, depending upon this calculation, at that particular location, we keep a breaker which is having more capacity than this fault current. Okay. So, the main purpose of fault analysis is to design the ratings of the protective switchgear that we have to install in the power system network. Okay. The different kinds of faults are the open circuit faults, short circuit faults, and other kinds of faults. Open circuit faults, short circuit faults, and other kinds of faults. The first one is, since our power system is a 3-phase network, if one conductor in 3-phase system gets open circuited, that is, if R phase conductor gets open circuited, the remaining 2 are healthy, then it is called a single line open circuit fault. It is a fault. Single line open circuit fault. Okay. So in the 3-phase power system, at any point, maybe it is at the generator, in the transmission line, in the feeder, in the transformer, wherever it is, if 2 conductors get open circuited, then it is called double line open circuit. Fault. Both are faults. Unsymmetrical faults. Both these are unbalanced or unsymmetrical faults. Any fault that creates unbalance in the system is called unsymmetrical or unbalanced fault. Suppose if 3 conductors gets opened, that means all 3 conductors gets opened, then it is not considered as a fault. It is not a fault. We simply call this one as a open circuit. The circuit has open circuit. It is not a fault. It is not a fault. We simply call this as a open circuit. So mainly this open circuit faults occurs in jumpers. That means during, suppose this is one tower, this is adjacent tower. Between these two towers there will be jumpers. So in summer, these jumpers, due to uneven expansion, if heat increases, there is a chance that this may get cut. One conductor, there is a chance that they may get cut, the jumpers may get cut. That will lead to open circuit fault. Okay, understand? So single line open circuit fault, double line open circuit fault, both are unsymmetrical faults. Whereas if three conductors are opened at any point in the power system, then it is not a fault. It is simply termed as an open circuit. Any doubt here? Okay. What are the undesirable effects of the open circuit fault? What happens if open circuit fault? The first one, we have seen that power system will enter into unbalanced operation. Power system will enter into unbalanced operation. Out of three phases, if one phase gets disconnected, or two phases get disconnected, the power system will become unbalanced. Okay. So during open circuit faults, voltage of the healthy phases will rise above their nominal values. Voltage of the healthy phases will rise above nominal value. There is a chance, if your grounding is not proper in an ungrounded system, if one of the line gets open circuited, what happens? The voltage of healthy phases will rise above nominal values, and there is a possibility of insulation failure. There is a possibility of insulation failure. That means, in this case, if this conductor is open, then the voltage of Y phase conductor and B phase conductor, it will overshoot. They will face over voltage problem. So there is a chance of insulation failure for the equipment that are connected to these two phases. Okay. Next, all three-phase induction motors require three-phase supply. 70% of the power system load is a three-phase induction motor. So when one phase gets connected, it will enter into single-phase operation. So all the three-phase induction motors are delta connected. Most of them are delta connected. So for a delta connected, this one, if one phase, suppose this is R phase, this is Y phase and B phase. If one of the phase gets disconnected, then it will enter into single phasing. This is called single phasing. Okay. So whatever the phase that is disconnected, okay, this winding will get burned. This winding will get overheated. That is called single phasing. So that is one major problem. Next, all the customers who are drawing from the R phase will get affected. Suppose my house is getting supply from R phase and there is an open circuit fault in R phase, then I will not get the power supply. All the customers who are getting power supply from that phase will get affected. So these are some undesirable effects of the open circuit faults. Okay. Next, short circuit faults. Short circuit faults. Again, the short circuit faults are classified into symmetrical or symmetrical short circuit faults. Symmetrical means balanced, and unsymmetrical short circuit faults. Okay. Symmetrical short circuit faults are line to line triple L fault. That means there is a short circuit between all three conductors of the line. It may be any place. It may be at generator or in transformer, in transmission line. If all three conductors are dead short circuited, it is called triple L fault. It is a balanced fault. Okay. The second one is if all three conductors are short circuited and touching ground. This is called triple LG fault. Triple LG fault. So both are balanced faults. Both are balanced faults or symmetrical faults. Okay. Next, unsymmetrical faults are, so if one of the conductor is touching ground, remaining two conductors are intact, then it is called LG, single line to ground fault. The second one is, if there is a short circuit between any two conductors, if there is a short circuit between any two conductors, then it is called line to line fault. Third one is, there is a short circuit between two conductors and these two conductors are intact, in turn touching with the ground, then it is called line to LLG fault. LLG fault. So these three are the unsymmetrical or unbalanced faults, whereas these two are the symmetrical faults. One more point which I want to convey is, if there are 100 short circuit faults, if there are 100 short circuit faults, out of which 80% or 80 of them are LG faults, the most common short circuit fault is the LG fault. Okay, 9% of them will be line to line fault. 7% of them are the LLG fault. Only these three included will be only 3 to 4%. Very rarely you will have a triple L or triple LG fault. Okay. So out of 100% faults, 80% are the LG faults, which mostly occur due to failure of pin type insulator. They occur mainly due to failure of pin insulator. Okay, pin insulator. The most common short circuit fault is LG fault, and the most uncommon or most rare fault is triple L and triple LG fault. Okay. Last discussion for today is, what are the undesirable effects of the short circuit faults? During short circuit faults, the power system components carry abnormally high currents, which are 5 to 10 times full load currents. During short circuit, see, whenever short circuit, again the current has to generate from the generator and it has to flow through all the components that are connected in series to the point. Suppose if I take, for example, this is a generator, this is a transformer, this is a transmission line, there is one more transformer. So here there is a short circuit. Here load is there, but before that there is a short circuit. Now you can imagine, during short circuit, the generator is carrying short circuit current, the transformer is carrying short circuit current, the transmission line, this transformer, everyone is carrying these short circuit currents. From the source, that is from the generator to the short circuit point, all the power system elements will carry this fault current. So these fault currents are 5 to 10 times. So 5 to 10 times the normal full load currents carried by the power system components. Normal full load currents carried by the power system components. Okay. Now if you remember one fundamental physical concept, if two parallel conductors are carrying current, say I1 and I2, separated by a distance d, then they will exert a force of attraction. Same direction, the force of attraction will be there. If the currents are in opposite direction, then the force of repulsion will be there. Okay. So anyhow, either force of attraction or repulsion, this force is directly proportional to the product of the two currents and inversely proportional to the distance between the two conductors. Distance between the two conductors. Okay. So if identical direction means force of attraction, if the currents are in opposite direction, then force of repulsion. Okay. And the second point is, the heat generated by current carrying conductor is given by I square into R. I square into R. Okay. Now, when they are carrying normal currents, say full load currents, then the force of attraction will be certain newtons, so many newtons, let us say 100 Newton. When a circuit breaker is carrying, or a transformer conductors are carrying, or transmission conductor, if the force of attraction or repulsion is 100 Newton. So for full load, the force of attraction or repulsion is 100 Newton. So I design my body of the transformer or a generator or a bus bar such that it can withstand 500 Newton. It can withstand 500 Newton, so that there is a factor of safety of 5. Factor of safety of 5. So even when it's carrying full load current, let us say 1000 watt is the heat dissipation. So I provide a heat sink, that is dissipation capacity of say 5000 watt or say 3000 watt, so that there is a clear dissipation and the equipment will not get overheated. So that's how I design my equipment. Estimating full load operation, I provide some cushion for heat dissipation as well as some cushion for the forces. Okay. But when fault occurs, the power system carries say 10 times the full load current. When it carries 10 times the full load current, then 10 I square into R, my heat generation becomes 100 times. My heat generation becomes 100 times. Even my force of attraction or repulsion, if I multiply both currents with approximately 10, it will become 100 times. Okay, so when you generate a heat which is 100 times the rated capacity, and when there is a force of attraction of 100 times the rated force, then what will happen? The equipment will damage permanently. The equipment will damage permanently. Why? Because you might not have seen, I have seen in one of the transformer, there was a short circuit. The breaker, because of some reason, did not trip. The bolts, the plate of the transformer, inside bolts, everything came at such a force that you don't know, it's even faster than from the trigger of a gun. So bolts just came like bullets and they pierced into the wall and they made holes in the walls. Fortunately, nobody was in line with that force. Okay, such will be the force generated. Your bus bars will weld and get melted. The two bus bars, when the fault occurs, if your breaker does not clear the fault, the two bus bars will just go and attach with each other and they get melted. So such will be the amount of heat generation, such will be the force of attraction or repulsion between the two parallel conductors. Understand? So if you don't clear the fault, within 100 to 200 millisecond, not even 1 second, 100 to 200 milliseconds, your equipment is permanently damaged. Your equipment is permanently damaged. You have to buy a new equipment. Understand? So such is the severity of these short circuit faults. So during short circuit, the power system components carry abnormally high currents, 5 to 10 times. These high currents generate enormous amount of heat because of heat dissipation and enormous amount of mechanical forces which will permanently damage the equipment. So power system equipment which are very costly and very bulky, the size of the equipment is very big and even they are very, very costly. So for these power system equipments like generators, transformers, transmission lines, bus bars, circuit breaker, all the equipment must be protected against the flow of short circuit currents. So whenever short circuit occurs, these equipment must be disconnected from the fault by means of circuit breakers and relays. So determining the rating of circuit breakers at a particular location is the primary objective of the fault analysis. So my breaker should protect the equipment without getting damaged. So I have to properly design my circuit breaker rating. That is the primary focus of the fault analysis. The first topic for today is what is the philosophy of a short circuit fault? So why short circuit fault currents are higher? What creates the severity in the when a short circuit occurs in a power system network? Okay. So if we model a power system, it will be a simple voltage source followed by generator impedance, followed by transformer impedance, followed by transmission line impedance, and then there will be a load. There will be a load. Understand? So this is load impedance. This is line impedance. This is transformer impedance. Suppose if there is one more transformer in step down, we are adding all the transformers that are in series together, and this is generator impedance or generator impedance. So let the source voltage be Vs. So when the system is operating without any fault, then the current carried by the components, is called full load current. Is called full load current. Suppose if the power system is operating at rated load, then what are the currents that is flowing? The generator is supplying full load current, and this full load current will flow through all the elements and it will return back to the generator. Okay. So my full load current will become source voltage divided by all the impedances, that is generator impedance. So let me call this before all the impedances except the load impedances, except load impedance, are called system impedances, So here the system impedance is a series combination of generator impedance, transformer impedance, and transmission line impedance. So we are defining Z system is equals to the series combination of generator impedance, transformer impedance, and transmission line impedance. Suppose there are multiple lines, the transmission line impedance includes the transmission line, feeder, distributor, everything. Similarly, transformers, all the transformers that are in the series, and this is the source impedance. Okay, so the full load current will become Z system plus Z load. So this is the full load current that flows in the system. Okay, so one more important point or one more important feature which you have to recollect, which you want to remember, is that in all the system elements, the reactance is very much greater than the resistance in all the elements. That means in generator, in transformer, and in transmission line, the reactance is very much greater than the resistance. So for all practical purpose, what we do, we neglect the resistance in all the system elements. So we neglect resistance parameter in system elements. That's why when you see the per unit impedance diagram also, all the elements are represented by the reactances only. Why? Because in these elements, the resistance is very small when compared to reactance, so we neglect them. Okay. And the second point, in load impedance, if you observe, in load impedance, resistance is very much greater than the reactance. In load impedance, resistance is very much greater than the reactance. Okay, that's why the full load power factors are 0.8, 0.9, and they are approaching near to unity. Okay, now when compared to the load impedance, Z system is very small. Z system is very small because the impedances of this generator, transformer, transmission line are very small when compared to the load impedances. So for all practical purpose, the full load currents the full load currents, we can approximately write it as system voltage divided by load impedance. System voltage divided by load impedance. Why? Because the system impedance is very small when compared to the load impedance, and in system impedance, resistance is very small when compared to reactance, so we neglect resistance. In all the system elements. Okay, but in load impedance, resistance is greater than reactance. When you compare these two, so because the system impedance is very less when compared to load impedance, your full load current, the full load current is, we are writing it as system voltage divided by load impedance approximately. Okay, so your full load current has two parameters, mainly resistive, because in load impedance resistance dominate the reactance, so mainly resistive current is mainly resistive in nature, and its value is high. Why its value is high? Because the jet load impedance value is high when compared to the system impedance. But the generator, transformer, and line. Now tell me, what is a fault? Fault occurs before the load. A short circuit that is occurring before the load is called a fault. Suppose a short circuit occurred here. Now, what is the impedance seen by the fault? The fault current, what is the impedance seen by the fault? It only sees the system impedance. So the current now flowing, it will flow in this path. Okay. So my fault current IF, is V system divided by Z system. So what is the feature of this fault current? If you completely neglect the resistance in the system elements, then it will be purely inductive current. And is large. Is purely inductive. Why? Because we have completely neglected the series resistance in all the system elements, and is large. Why? Because the system impedance is very small. When compared to the load impedance. That's why your fault currents are very much greater than the full load currents. Okay. Why? Because the impedance seen by the fault is very small when compared to the actual impedance when the system is healthy. Why again the fault current will vary? Suppose if the fault occurs here, then the total impedance seen by the fault is the series combination of generator impedance, transformer impedance, and line impedance. Suppose if the fault occurs here, then it only sees the generator impedance. Understand? So as the fault occurs closer to the source, the intensity of the fault increases. As the short circuit occurs closer to the source, the intensity of fault increases. Understand? The fault intensity will increase. That means the fault current will increase. So the most dangerous fault is the fault at the terminals of the generator. The least severe fault is the fault which is occurring at the terminals of the load. Okay. So likewise, the fault current also keeps on varying depending upon the location of the fault. So two important points which you have to remember is full load currents are mainly resistive, and their full load current values, full load currents, full load impedance value is high, full load currents are small, full load currents are small. Whereas fault currents, the impedance seen by the fault is very less. So the fault currents are purely inductive. Why? Because we neglect the resistance, and the fault currents are very large. So that's why we mentioned the fault currents are 5 to 10 times the full load currents. This is the philosophy of the short circuit fault. Okay. So any doubt in this section? Okay. So next is assumptions made during short circuit fault analysis. Okay. The first point is full load currents are 5 to 10 times the fault currents are 5 to 10 times full load currents, and fault currents are mainly inductive. Why? Because we have already know the reason. Fault currents are mainly inductive, and full load currents are mainly resistive. So both are out of phase. Resistive current and inductive currents are 90 degrees out of phase, and full load currents are neglected during fault analysis. To make the analysis simpler, fault analysis simpler, what we do is we neglect the full load currents during short circuit fault analysis. The two main reasons why we neglect the full load currents during fault analysis is the magnitude of fault currents is very high when compared to full load currents. First reason. Second reason is full load currents are mainly resistive, whereas fault currents are mainly inductive. So there is a phase difference between them. There is a phase difference between them. For example, just for our understanding purpose, if my full load current in any load is 10 at an angle minus J 5 ampere, this is the full load current, where resistive current is more, inductive current is. Suppose the fault current on the same system at the same location is 0 minus J 100 ampere. 0 minus J, say let us say it is 100 ampere. Okay. Now the actual current that flows immediately after the fault is the addition of these two. Addition of these two. So that is 100 minus J105. This is the actual fault current that will flow immediately after occurrence of fault. But however, what we do, we assume this full load currents are zero. We neglect them, and we take the total fault current as 100 ampere, J100 ampere. So there is some error, but however, this error is less than or equal to 5%. The error is very small because of the actual current and the fault current. Okay. So to make the analysis simpler, we assume the full load, we neglect the full load currents. Okay, that is the point. So pre-fault conditions, we assume that pre-fault conditions are no load conditions. That means we assume before occurrence of the fault, our power system is operating under no load condition. We assume that before fault, our power system is on no load. This is the first assumption that we make in the short circuit fault analysis. Okay. The next assumption is the magnitude of line charging currents and the magnitude of leakage currents. Line charging current is the current that flows through the shunt capacitance, which we have studied in transmission lines, where we have written IC is equals to C parameter into V phase. This is the line charging current. Which is usually very, very small. And one more current, leakage current, is the current that flows through the insulator string and to the from the conductor through insulator string to the tower, where we have written while discussing the shunt conductance parameter, this is V phase divided by insulation resistance of the stream, which is very small. Okay, this will be approximately in the range of few amperes. This will be in the range of few milliamperes. Okay, so both these values are very small when compared to these line charging current and leakage currents in the overhead transmission line are very small when compared to the full load currents. Okay, when compared to fault currents, they are very small. They are very small when compared to fault current. So we neglect the presence of both these currents while we are doing fault analysis. We neglect the line charging currents and the leakage currents during the short circuit fault analysis. So it flows through shunt capacitance, it flows through shunt conductance. So if we are neglecting these two currents, that means we are completely neglecting the shunt admittance parameter of transmission line. We are completely neglecting the shunt admittance parameter of transmission line during fault analysis. So shunt admittance parameter of transmission line is completely neglected during short circuit fault analysis. That is the second assumption. Okay. The third point is the third assumption which we make is we have already discussed the resistance parameter in generator, transformer and transmission lines. It is very small when compared to the reactance parameter, so we neglect it. So we neglect the resistance parameter in generators, transformers and transmission lines. Okay. So with above assumptions, our power system networks becomes purely reactive, that it becomes purely inductive, and the power factor of the fault current will become ZPF lag. Okay. So how the system will be if we make all this assumption, we have already seen in the per unit impedance diagrams. Okay. So the network becomes purely reactive, and what is the power factor of the fault current? It is ZPF lag. Why? Because we have neglected the resistance parameter in all the system elements. Okay. Now, if we consider the resistance parameter in the system elements, then the fault current, the power factor of the fault current will be in the range of 0.1 lag to 0.2 lag. This is a note. Suppose if someone asks in objective questions, if you completely neglect the resistance, it is ZPF lag. If you consider the resistance of the system elements, then the power factor will be 0.1 to 0.2 lag. Okay, these are the assumptions made during the fault analysis. Again, I am repeating one after the other. The first assumption is we completely neglect load currents. That is, we assume before fault our power system is under no load condition. First assumption. Second assumption is that we neglect the line charging currents. This is the second assumption. We neglect the line charging currents and leakage currents. So that means we are neglecting the shunt admittance parameter of the transmission line. We are neglecting the shunt admittance. Third assumption is that we neglect the resistance parameter in the system elements like generator, transformer and transmission line, which makes our power system network purely inductive, and power factor of the fault current is ZPF lag. These three assumptions which we make during short circuit fault analysis. Okay. Next, what is a symmetrical fault? What is symmetrical fault? So if the fault affects all three phases equally, then it is called a balanced fault or symmetrical fault. So what are the symmetrical short circuit faults? LLL and LLL triple LG. Okay, so these are the balanced faults, balanced short circuit faults. Okay. Second point is, since the power system is balanced during the fault also, we do the analysis only between one phase and neutral. Why? Because the fault is affecting all three phases equally. So if we do the analysis on one phase, then the same results will be applicable to the other two phases. Usually we will do analysis between the reference phase, that is R phase, and neutral. The third point is, since the power system network is balanced during the fault, it is balanced before the fault, during the fault, and even after clearing the fault. So when a symmetrical fault occurs, the power system is balanced before fault, during fault, and even after clearing the fault. So the potential of neutral and ground is zero all time. The potential of neutral point and ground is zero all the time. So all the impedances that are connected between neutral and ground are neglected. All the impedances that are connected between the neutral and ground in all the elements is neglected during symmetrical fault analysis. Okay. One more point which I want to tell you is that there is no difference between triple L and triple LG fault analysis. Why? Because suppose if you take the system, if the fault occurs here, this is IA, IB, IC. If all these fault currents are balanced, then the sum of all these balanced fault currents is how much? 0. The phasor sum becomes 0. Even if it is grounded, in this case triple LG fault, this is the fault. Now what is the current that is flowing through the ground? Current flowing through the ground is sum of IA plus IB plus IC, that is equals to 0. So in triple LG fault, the ground does not carry any current. So that's why the current flowing through this path is 0. So there is no difference between the analysis of triple L and triple LG fault. Many people think that some current will flow through the ground in triple LG fault, but absolutely no current will flow through the ground. Understand? So analysis of triple L and triple LG fault is exactly same. And second important point is, current flowing through the ground is 0 during triple LG fault. Understand? Okay. Next, procedure to carry out the symmetrical fault analysis. First step is to convert single line diagram into per unit impedance diagram. The first step is to convert the single line diagram into per unit impedance diagram. That is the first step. Okay. Second step is identify the location of fault. Identify the location of fault in the per unit impedance diagram. Okay. Third step is determine the Thevenin's impedance between fault point and reference. Determine the Thevenin's impedance between fault point and reference in the per unit impedance diagram. Let us call that impedance as, that Thevenin's impedance as X1 equivalent. X1 equivalent. Why? Because the Thevenin's impedance, I am calling it as X1 equivalent. What is this impedance? It is the Thevenin's impedance between the fault point and reference in the per unit impedance diagram. Okay. The Thevenin's voltage can be directly taken as 1 per unit. The Thevenin's voltage can be directly taken as 1 per unit. Okay. Now, the fault current in per unit is given by Thevenin's per unit voltage, which is 1 at an angle 0, divided by Thevenin's per unit impedance between fault point and reference. This will give you the per unit fault current. So if you want actual fault current, then you have to multiply per unit fault current into I base current of the fault location. So fault location will have some base current. With that I base you have to multiply. Okay. Next, the short circuit MVA of that fault is given by short circuit MVA is given by base MVA. While converting per unit single line diagram into per unit impedance diagram, you will be having one base MVA. So but you have to multiply that base MVA with simply per unit fault current. Then that will give you the short circuit MVA of the fault. Okay. So only there are 4 steps. If you carefully observe, the first step is convert the single line diagram into per unit impedance diagram, which you already learned. Next, identify the fault location in per unit impedance diagram. Okay. Identify the fault location. And third step is determine the Thevenin's per unit impedance between the fault point and reference. Reference is neutral in this case. Okay. Then Thevenin's per unit voltage can be directly taken as 1 per unit. I'll explain why we have to take 1 per unit. Next, per unit fault current is given by 1 divided by x1 equivalent. And short circuit MVA is given by base MVA into IF per unit. Base MVA into IF per unit. Understand? So this is the procedure to calibrate the symmetrical fault current. So here why we are taking the Thevenin's voltage as 1 per unit cell? Because pre-fault condition is no load condition. That means before fault the system is not carrying any current. When the system is not carrying any current, just for your understanding I am telling, let me take a simple diagram. Suppose this is my Thevenin's impedance diagram. This is the fault location. Okay, this is 1 at an angle 0. Let us call this one as J1, J0.5 and J0.5. Okay, so this is the per unit impedance diagram. This is the fault location. Now third step is we have to compute the Thevenin's impedance between the fault point and reference, that is neutral. So that value will become x1 equivalent. That value is how much? In this case, so to calculate the Thevenin's impedance, what you do, you short circuit the voltage source and calculate the equivalent impedance. This value will become how much? This is J1 ohm in parallel with J1 ohm. It will become J0.5. Okay, J0.5 per unit. Now, since I am assuming my power system is under no load before fault, so what is the current that is flowing in the system before occurrence of fault? 0. So here also current 0, here also current 0, here also current 0 before fault. So what is the voltage drop here? Voltage drop here also 0, here also voltage drop 0, here also voltage drop 0. So the voltage at this point is same as voltage at this point and voltage at this point. Okay, that's why I can directly take my Thevenin's voltage, the Thevenin's voltage as 1 per unit. I am taking directly my Thevenin's voltage as 1 per unit because before fault I am assuming the system is under no load. When the system is under no load, the impedance drop between all the reactances is 0. So voltage at all points is 1 per unit. Voltage at all points is 1 per unit. Understand? That is the point. So I am taking my Thevenin's voltage as 1 per unit. So my short circuit, my fault current will become how much? 1 at an angle 0 divided by J0.5. This is minus J2 per unit. So minus J symbol will tell it is purely inductive current. So if you want only magnitude, it is 2 per unit. My fault current is 2 per unit. Okay. So for this system, let the base MVA is, for example, let us take base MVA is 50 MVA for this one. Now our short circuit MVA will become, base MVA into IF per unit, that is 50 into 2 per unit, that is 100 MVA is the short circuit MVA of the fault. of the fault. Understand? So this is how you compute the symmetrical fault analysis. This is how you carry out the symmetrical fault analysis. Okay. Now, one important note is in fault analysis we neglect all the loads, understood? But we cannot neglect the synchronous motor except synchronous motor. Why? Because synchronous motor acts as a synchronous source during the short circuit. Synchronous motors, because they are having internal EMF, so synchronous motors acts as a sources that supplies the fault current during fault analysis. So we cannot neglect synchronous motors in short circuit fault analysis. Okay, all induction motors, lamp, resistive loads, everything you can neglect, but you cannot neglect the synchronous motor. Why? It has the capacity to supply the fault current. The second thing is, during fault, to calculate the fault current, we have to use the subtransient reactance of synchronous machine. So why? We will see in the coming sections. Okay, we have to use the subtransient reactance of the synchronous machine to calculate fault current. Okay. The third important note is to calculate the breaking current of the circuit breaker. To calculate the breaking current or interrupting current of circuit breaker, we have to consider subtransient reactance of generator, and transient reactance of motor. Okay. So these points you have to remember, very important points. So now let us take few problems and then we'll continue to the further discussion. Let someone read and try to solve this question. To a bus bar, 4 identical generators are connected. So generators, how we model in per unit impedance diagram as a series combination of reactance and a voltage source. So how many generators are connected? 4. So they are all connected to the same bus. This is the bus. Now he's asking the short circuit MVA capacity of this bus. So how do you model in per unit? All sources is voltage is 1 at an angle 0, that is 1 per unit. Now he said that the subtransient reactance of all the generators is 16%. So what is the per unit subtransient reactance? Percentage reactance by 100. So it will become J 0.16 per unit, J 0.16, J 0.16, J 0.16. Okay. Now I have to calculate the short circuit MVA of this bus. So for that you have to simulate a short circuit. So if a short circuit occurs here, then what is the short circuit MVA that occurs in this faulted pump? That is the question. Okay. So now what we have to do? First we have to calculate the per unit fault current. Per unit fault current is how much? IF per unit is equals to 1 at an angle 0. Thevenin's voltage directly you can write it as 1 at an angle 0 we told, and X1 equivalent. Thevenin's per unit impedance between this point and this one. So if you calculate the Thevenin's impedance between, these 2 points, so what will be the Thevenin's per unit impedance? You have to short circuit all voltage sources and all the impedances are connected in parallel. So your X1 equivalent will become J 0.04. Okay. So if you calculate your fault current, it will become 1 divided by only magnitude to calculate. 1 divided by 0.04, it is how much? 25 per unit. And what is the MVA rating of each machine? 20 MVA. So short circuit MVA, that is equals to base MVA. Here base MVA is nothing but the generator rating into IF per unit. So base MVA of each machine is 20 into IF per unit is 25. So short circuit MVA is 500. So option A is the right option. Option A is the right option. Understood? To calculate short circuit MVA in such cases, when you have anything, some identical elements connected in parallel, base MVA divided by X1 equivalent. Short circuit MVA is also given by base MVA divided by X1 equivalent. So directly you can write, if you write 20, 4 alternators connected in parallel, everything 0.16, you can write 0.04, you will get 500. Always better follow procedure. Okay, shortcuts sometimes they may work and they may not work. That's why I never teach shortcuts. Okay, one generator is connected to a transformer through a circuit breaker. Okay, this generator rating is 110 MVA, 11 kV, and its direct axis reactance is 130%, and subtransient reactance, that is XD double dash, is 26%. So what he's telling, if a short circuit occurs between the three-phase short circuit occurs between the breaker and the transformer, then what is the fault current that what is the initial fault current that flows through the circuit breaker? What is the initial symmetrical short circuit current that flows through the breaker? Okay, so if you draw the per unit impedance diagram here, it's very simple. If there is one only generator is there, after that circuit breaker is there, and then you have a short circuit. Okay, so this per unit voltage is 110 angle 0. So for calculating fault current, we have to consider the subtransient reactance of generator that we have already seen in one of the note. So for calculating the fault current, while calculating the fault current, you have to take the subtransient reactance of synchronous machine. So it will become 26%, means in per unit it will become J0.26. So now your IF per unit is how much? Your IF per unit is 1 divided by 0.26. If I am only taking the magnitude. 1 divided by 0.26 would be how much?
3.846.
3.846 per unit. Okay. So this is the per unit fault current, but I want actual fault current. So IF actual is equals to IF per unit multiplied by base current. So where the base current in the generator circuit. So this is given by 3.846 multiplied by, to calculate base current, what is the formula we have already discussed in the previous class? SB divided by √3 into base voltage. So here base MVA is 110 MVA, three-phase base MVA is 110 MVA divided by √3 into the base voltage is 11 kV. So if you do that, so many kiloamperes will be your short circuit current. So if you calculate how much you're going to get, 3.846 multiplied by 110 divided by, it will become 10 divided by √3. So many.
22.2.
How much?
22.2.
So 22.2 kiloamperes is the fault current that flows through the system. 22.2, this one. Okay. So it's one more model question, very easy question. Here the network we don't know. It is a simple power system. It is a power system network whose fault current is 8 per unit. So any unknown network, how you model it as a series of Thevenin's circuit. That is one voltage and one reactance. So the complete power system network I am writing in the Thevenin's model, where my Thevenin's voltage is 1 at angle 0, my unknown reactance is X per unit, and here is the, if the fault occurs, here's what he is telling, the fault current is 8 per unit. The fault current is 8 per unit. So in order to reduce the fault current to 5 per unit, he wants to connect one series reactance. So what is the value of that series reactance? That means he wants to make the system like this. So 1 at an angle 0, this is the existing system, what you are getting after Thevenizing. This is X per unit. So I am adding one more series reactance so that my fault current in this case will become how much? 5 per unit. Now can you please tell me what is that series reactance value? That is the question. Very simple. So from this you are getting IF is equals to magnitude only 1 divided by X is equals to 8. So which implies X is equals to 1 by 8. That is 0.125 per unit is your X value. Okay. So from this what you are going to get? Your IF is equals to 1 divided by X plus X series. This is equals to 5 per unit. So from this you are going to get X plus XSC is equals to 1 by 5, that is 0.2 per unit. Okay. Now this X value we already know 0.125 plus XCSC is equals to 0.2, which implies XCSC value is how much? 0.075 per unit. 0.075 per unit. So this is the value of series reactance that we need to connect to reduce our short circuit current from 8 per unit to 5 per unit. So this is your right option. Understood?
Yes.
Yeah, the trick is how to model an unknown system. Unknown system, you always model it as a Thevenin's voltage in series with the Thevenin's impedance. So again, if you understand, there are two alternators that are connected by a bus bar. So circuit will be, this is one alternator that is connected to one bus. This is one more alternator that is connected to one more bus. And these two buses are interconnected through a reactor. Okay. Now he's asking the equivalent impedance to fault current for a three-phase fault and an alternator bus will be the equivalent impedance. So what is the equivalent percentage impedance to the fault current for a three-phase fault that is occurring on any buses? So very simple. If you draw the per unit impedance diagram for the system, so every alternator, how you can model? This is how you model first alternator. And this is the bus bar. And this is your second alternator. Why I am drawing this ground and neutral, everything is same potential. So these two you can join. Okay. The bus bar of each of the alternator is 15% reactance. So this is 1 at an angle 0, J 0.15, J 0.15, 1 at an angle 0. Now what is the, are interconnected through a tie bar whose reactance is also J 0.15. Okay. Now what is the Thevenin's equivalent per unit impedance if the fault occurs at this point or fault occurs at this point? So if the short circuit occurs at this point or this point, what is the Thevenin's equivalent impedance? That is the question. Okay, very simple. You have to calculate the Thevenin's impedance between X1 equivalent between these 2 points. You will get exactly same value whether you do it this time or this time. So if you short circuit voltages and calculate this one, This will be X1 equivalent will become directly, I'm writing 0.3 in parallel with 0.15. So this is 0.3 into 0.15 divided by 0.45. Okay. So 2, 3. So it will become 0.1. In percentage, it will become 10%. So option B is the right option. Option B is the right option. Have you understood? This is tie bar. This reactor is called a tie bar, which ties the two buses. Yeah. Come on, yaar. Very simple question. So there is one synchronous generator which is connected to a transformer, and then there is a bus bar, and then there is a bus bar. So if the short circuit fault occurs on this bus bar, if a three-phase short circuit fault occurs on this bus bar, what is the short circuit MVA? That is the question. Okay. So how you can draw the per unit impedance diagram? First is a generator, next is the transformer, and next is the fault location. Okay. One at an angle 0. This reactance is 0.1 per unit. Transformer also 0.1 per unit. Now he's asking short circuit MVA. First to calculate IF per unit. IF per unit is 1 divided by J2. So if you want only magnitude, it will become how much? Sorry, J0.2. I'm sorry. J0.2. So this will be 5 per unit. Since both the generator MVA is also 100 MVA and the transformer MVA is also 100 MVA, we can take our base MVA as 100 MVA. So short circuit MVA will become base MVA into IF per unit. So this value will become 100 into 5, 500 MVA. So symmetrical fault analysis is very easy. First, you have to draw the per unit impedance diagram, identify fault point, and compute the per unit fault current. That's it. Okay. Short circuit currents are much smaller than load currents, yes. And short circuit currents are purely inductive. Load currents are mainly resistive. So they are greatly out of phase. So both option 1 and 2, this is the right option. We have told just before that this is the main reason why we neglect the short circuit load currents in short circuit calculation. Why? Because first thing is short circuit currents are much larger than the load currents, and short circuit currents are 90 degrees out of phase, approximately 90 degrees out of phase with the load currents. Both the reasons are correct. Yeah, one more question. Can you take this one? First, imagine how the system is. There is one generating station which is connected by a transmission line. This is station 1, which contains only one generator, and this is the transmission line. And here there is a station 2. Station 2, which contains two generators. So this is station 2. This is the transmission line. Okay. So it's telling the fault is occurring exactly in the middle of the transmission line. Okay. So how, if you draw the per unit impedance diagram, very simple. So this is one generator. This is a transmission line. This is substation, station 2, which has two generators. Okay. 1 at an angle 0. Generator 1 has a reactance of 0.2. That line has a reactance of 0.4. And station 2 has two generators of reactance, J0.4 and J0. Okay. So fault is occurring where? Fault is occurring exactly middle of the transmission line. Exactly middle of the transmission line. A three-phase short circuit fault is occurring. Three-phase short circuit fault is occurring. So what is the change in the value of equivalent fault reactance with one of the generators of S2 is removed? Very complex question. What is telling? What will be the change in the equivalent reactance, equivalent fault reactance with one of the generators of S2 removed? So first you have to calculate original fault impedance. For original fault impedance, you have to imagine the fault is here. That means this one you have to write half of the transmission line reactance is here and remaining half of the transmission line reactance is here. It is J0.2 and J0.2. So first you calculate this Thevenin's reactance in the first case. You calculate this one, what you are going to get? X1 equivalent in original case. These two are in series, these two are in parallel, which is in series with this one. Again, both are in parallel. So it will become 0.4 in parallel with 0.4. So that will become 0.2 per unit. If you're good at circuits, you can directly tell it. First, these two are in series, it will become 0.4. These two are in parallel, it becomes 0.2. Again, 0.2 plus 0.2, 0.4. Again, both are in parallel. So it will become 0.4 in parallel with 0.4, 0.2. Now, the second case is that when you remove one of the generators, when you remove this one of the generators, now he's asking what is this one. So in this case, what it will become? It will become 0.4 in parallel with 0.6. Okay, this is the X1 equivalent after case 2. So can anyone tell 0.4 in parallel with 0.6? It will become 0.24. 0.24 per unit. Okay. Now, I hope I am right. 0.24. Yeah. Now, what is the change here? From this to this, what is the percentage change? So this will become 0.04 divided by 0.2 into 100. This will be 20%. Change is 20%. So the next topic and today's last topic is three-phase short circuit on a no-loaded power system network. So what happens if a three-phase short circuit occurs on a no-loaded power system? Okay, now let us take a power system as a generator. There is one transformer, step-up transformer, transmission line, again step-down transformer, again load will be there. This is how an approximate power system will be there. Let us assume we have disconnected the load. We have disconnected the load, and here when the power system is under no load, a three-phase short circuit has occurred. A three-phase short circuit has occurred. So when the three-phase short circuit suddenly occurs, then how the system behaves, what are the fault currents we are trying to understand. Okay. So since we have completely neglected the series resistance parameter, since we have completely neglected the shunt admittance parameter in fault analysis, The entire circuit I can model it as a, the entire circuit in single phase I can model it as a voltage source in series with some resistance and some inductance, and here there is a switch. Here there is a switch. If I close, the short circuit will occur on the system. If I close this switch is closed at t equal to 0, then the short circuit, dead short circuit occurs on the system. So this is, let us call this as capital R and capital L, where capital R is the total series resistance of all the elements, total series resistance of all the elements from source to the fault point, from source to the fault point. Similarly, X is the total series reactance of all the elements from source to the fault point. Let this source voltage let us take it as Vm sin omega t plus alpha. Let our source voltage be Vm sin omega t plus alpha. Understand? Now, when the fault is occurring at t equal to 0. When the fault is occurring at t equal to 0. So then the total fault current, that is I of t, is what I am trying to calculate just immediately after occurrence of fault. So if you do the KVL by the Kirchhoff voltage law, what you are going to get? Vm sin of omega t plus alpha is equals to R into I of t plus L into di of t by dt. It is a first order non-homogeneous differential equation. For this, what is the solution? I of t is the solution. If you find out I of t, it has two components. One is the transient component, which I can write it as k into e power minus t by tau, plus this is the transient current, and the steady state current will be Vm sin of omega t plus alpha minus phi divided by mod z, where phi is equals to tan inverse omega L by R and mod z is equals to square root of R square plus omega L square, where this is the total series impedance and this is the phase angle due to lagging circuit. So this is the total current. This is called transient current. This is called steady state current. Okay. Understood. Just before and just after fault, that means at t equal to 0 minus and at t equal to 0 plus, what is the current flowing through this no loaded circuit before occurrence of fault? 0. Then what will be the current flowing through the circuit or through the system just occurrence of fault? Because inductor does not allow sudden changes in current. The current flowing in the circuit, that is the fault current just before occurrence of fault and just after occurrence of fault, I of t will become 0. I of t will become 0. Understand? So at t equal to 0 minus and at t equal to 0 plus, what we are having? Our I of 0 is 0 ampere. That means if you substitute t equal to 0 in this one, you're going to get I of 0 equal to k into e power minus t value is 0 plus Vm by mod z into sin of omega omega t, I am substituting t equal to 0, which implies alpha minus phi is equals to 0. I'm going to get this value. So from this, e power 0 is 1. So k value will become minus Vm by mod z into sine of alpha minus phi, which is, you can write it as, if I interchange these values, I can write it as k equal to Vm by mod z into sine of phi minus alpha. Okay, so if I substitute back into that one, my I of t will become Vm by mod z into sine of phi minus alpha e power minus t by tau plus Vm by mod z into sine of omega t plus alpha minus phi. So this is the total current that flows immediately after occurrence of fault. This component of current is called DC offset current. This is called DC offset current. Okay, which you can observe if you fix this magnitude, it is decaying in nature. So what is the nature of this current? This nature of this current is exponentially decaying in nature. Okay, so if this value is Vm by mod z into sine of phi minus alpha. So what is the nature of this current? This current exponentially decays with time. So this is the nature of this current because of e power t minus tau. So within 5 time constants, it will decay to 0. Okay. Now this is the symmetrical short circuit current, which is sinusoidal in nature. This is called symmetrical short circuit current. So which is sinusoidal in nature. If you draw this one, it will be of this nature. Okay. Sinusoidal current. Understand? So far we have calculated, that is IF per unit is equals to 1 divided by X1 equivalent. So far we have only calculated the symmetrical short circuit current. So whatever the formula that we have adopted during the previous example, whatever the current that we have calculated, that is the symmetrical short circuit current. We did not consider the DC offset current. Why this DC offset currents are coming? Because of the sudden occurrence of fault. So this DC decaying currents or DC offset currents are coming into picture. So when we are designing the switchgear, we have to consider both the currents. If you only consider symmetrical short circuit current, our estimate will become wrong. Our protection may fail. So while designing the circuit breaker, we have to consider both the DC offset current, which is transient in nature, and symmetrical short circuit current. Okay. So the only 2 points we have to remember in this article is, first point is, so far, the fault current that flows immediately after occurrence of fault contains 2 components. The short circuit fault current, which flows immediately after occurrence of fault, contains 2 components. One is DC offset current, the other one is symmetrical short circuit current. Okay. So this DC offset current is exponentially decaying in nature. After some time it will decay to 0. Okay. The second point we have to remember is, while for designing the circuit breaker, you have to consider both DC offset current as well as symmetrical short circuit current. Okay. Next. So the maximum value of fault current. So just immediately after occurrence of fault, what is the maximum value of fault current that can flow? Let us assume there is no decay. This is called IMMT, this is called a maximum momentary current. What is the term? Maximum momentary current. Momentary current. So this is the current that flows immediately just after occurrence of fault. So here in the first DC offset component, I am ignoring decay. It will become Vm by mod Z into sine of phi minus alpha. And here I am assuming the peak value Vm by mod Z. So this is the maximum value which can occur. So the magnitude, if I take, this can be the maximum value that can flow where my symmetrical component is showing its peak value and my DC offset component is also having no decay, and both are additive in nature. Both are additive in nature. So this is the maximum momentary current which can flow immediately after occurrence of fault. Immediately, this is the current. This is the momentary current that can flow immediately after fault. Understand? Now, what can be the highest value for this one? Highest possible value. Highest possible value for maximum momentary current is how much? The highest possible value occurs when phi minus alpha becomes 90, let us say. So in this case, IMM, maximum momentary current, maximum possible value. Maximum possible value. It will become how much? 2 times Vm by mod Z. 2 times Vm by mod Z. That is 2 times peak value of symmetrical short circuit current. So the peak value, what is the peak value of the short circuit current? Vm by mod Z. Vm by mod Z. So the maximum momentary current, the maximum possible value is how much? 2 times the peak value of symmetrical short circuit current. So current in any possible condition cannot exceed this value. So if I design my breaker so that it can withstand this value, so if I design my circuit breaker so that it can withstand this value, then it can withstand any condition. It will never fail. So for designing the circuit breaker, we consider the maximum possible value of maximum momentary current, which is 2 times symmetrical short circuit current, which is 2 times the peak value of symmetrical short circuit current. So if I design the circuit breaker to withstand this value, then it can withstand any fault current. So this is why we calculate this one. Okay. So how the waveform will look impinging. So symmetrical currents will be like this. So if your exponential component is added to that symmetrical short circuit current, then your waveform, the current waveforms will be like this. So the highest possible value you can see, highest possible value is 2 root 2 I RMS. He's telling 2 root 2 I RMS, where I RMS is the RMS value of the symmetrical fault current, symmetrical short circuit current. So whatever we have calculated currents, that is by using formula 1 at an angle 0 divided by X equivalent, these are the IRMS, symmetrical short circuit currents. Symmetrical short circuit currents. So usually we deal with RMS values. So again he has multiplied. This is 2 times the symmetrical short circuit current. Again, to get the peak value, he has multiplied with root 2. So if you see this one here, this highest possible value of this fault current can be 2 root 2 into I star. Okay, gradually after 5 time constants, what will happen? This current will decay. The DC offset currents have become 0. So the current will come to the normal value. Current will come to the normal value. Normal value means it is root 2 into IRMS, normal currents. Understand? So the concluding remarks is the fault current contains two components, the symmetrical short circuit current and the DC offset current. For selection of circuit breakers, momentary short circuit current is taken corresponding to its maximum possible value, which is a safe choice for designing the circuit breaker. Safe choice for designing the circuit breaker. Okay. So next topic is also lethargic. So we'll stop at this point. For tomorrow's class, you please, at least in YouTube or in Google, you read armature reaction and come. What is armature reaction in synchronous machines? What is demagnetizing effect of armature reaction? Demagnetizing effect. The second one is cross magnetizing effect. Just you read and come. What is armature reaction? How voltage is induced in synchronous generator? You just have an idea.